Okay, so shall we start? So today I'm going to tell about CFT in non-trivial maybe dependence on CFT on metric. And the Liouville theory. So let us study the free boson. So S of phi is the integral over, but here we need to write it here we want to write it in the arbitrary metric. So it is a square root of g times g mu nu d mu phi d nu phi. So there are Laplace equations. So there is a Laplace operator, which is what? It is 1 over square root of g, g mu rho d d rho. Oh no. So well, we can write mu g mu nu d nu d nu or plus n of phi, and this one d nu phi. Right. So in 2D, we can perform some coordinate change, which makes this metric diagonal. We can transform it to g mu nu equals to e to 2 sigma, let's call it sigma, times like g mu nu dx mu dx nu, can be written as e to the 2 sigma. I forgot which notation I've chosen. Probably with some factor. No, without anything. Yes, dz bar. So it's a kind of gauge fixing. And if we do this, then this action of phi, like and phi and g actually, and this action of phi and sigma becomes the integral over d to z. And we see that this square root of g and this g mu just cancel. It becomes d phi d bar phi. And the Laplace operator becomes what? Here on this cancels again, and we are left with 1 over square root of g. It is e to the minus 2 sigma d bar phi. So now we are interested in the following object. We want to consider a partition function which depends on sigma. So it is path integral over phi e to the minus s of phi sigma. And we want to ask what is the dependence of this partition function on sigma. So naively, we can say what that this action does not contain sigma explicitly. So let us just compute it as an integral of quadratic form. So we can say, but let us be a little bit more careful. So this action can be written as so it is integral over d phi e to minus e to the scalar product of phi times Laplacian of phi. Where this scalar product is defined in the following way. So a scalar product of f and g is the integral over d to z square root of g f times g. Well, everything is real, so we can consider just a real scalar product, and it equals to integral over d to z e to the 2 sigma f times g. So it is something which depends on sigma. And if you compute this integral, we should actually think what is the definition of this measure in this integral. So if you compute this integral, then it is some constant divided by the square root of a determinant of Laplacian minus Laplacian times, so here we have quadratic form in the numerator. So it is square root of Laplacian times a square root of determinant of this quadratic form. And we should say that the definition of measure d sigma phi is such that d sigma phi determinant of this scalar product is equal to 1. because this is something which is not invariant under the change of basis in the space of functions. So we should use some more or less canonical normalization of this path integral. So it means equivalently that if you consider this integral, the sigma of delta phi, some tangent vector delta phi, e to the minus scalar product delta phi times delta phi, this integral should equal to 1. So it is the definition of this measure in the path integral.
So it's basically like if we take the eigenfunctions of the Laplacian instead of
Yes. So the idea is the following: that when we work with the path integral, then the measure of integration is actually depends on the operator which we want to integrate, because we should have some way to define this. So we need some basis in this infinite dimensional space, and there is no other way to choose this basis other than to say that we are taking eigenfunctions of this operator. And we also say that these eigenfunctions are canonically normalized. So this is maybe a little bit different from the finite dimensional integrals, because there we have just some quadratic form, and we compute the determinant of this quadratic form. But here we should use the operator itself to define this measure. So so here it is, maybe if you look at this definition, then it looks like a little bit indirect use of the Laplace operator, because this metric which is written here is a metric in which this Laplace operator is self-adjoint. Because you see, if we just conjugate of this, it will differentiate to the minus 2 sigma. But if we choose such a measure, then it becomes self-adjoint operator, and it makes sense to take its eigenfunctions. So is it fine? Are there any questions about this? And the consequence of this is that this path integral in phi is just 1 over square root of determinant of Laplacian. It is much better defined as than determinant of some quadratic form. Now it does not depend on basis. So now this z of sigma is 1 over square root of determinant of minus Laplacian. So this object now does not depend on basis, so it is much better. And we can also consider logarithm of this. W of sigma is logarithm of 0 sigma, and it equals to, so by definition it equals to -1/2 sum of the eigenvalues of Laplacian. Eigenvalues of delta. Of minus Laplacian. So now this logarithms can be written as this following formula, which is which says that logarithm of x is integral from 0 from what to say, from epsilon to infinity, e to minus t minus e to minus tx over t dt. Let me think. Like in principle, this integral is from 0 to infinity, but we will modify it a little bit later. So we can write that it is sum over k, this integral from 0 to infinity, maybe plus 1/2 e to minus so e to minus t lambda k minus e to minus t dt. Okay, so this can be written as so if you take now sum of e to minus t lambda k, it is the same as to take a trace of the operator. So it equals to 1/2 integral from 0 to infinity dt over t trace of e to t times Laplacian minus e to the minus t. Maybe I don't remember precisely how it is called on this trick. Maybe it's due to Schwinger, but there is such representation for determinants, and now why it is nice. So actually you should put here some number in advance because we will see quite soon that it is this integral is divergent. So we add here some number epsilon, which does not affect small modes of Laplacian. So this epsilon should go to 0. But we need to regularize this expression somehow in advance. So we add such modification. And so if you substitute explicitly who is our Laplacian, but it is written there, maybe there is no need to substitute this. But now we want to study what happens when we start to change this metric. So let us consider W of sigma plus delta sigma. First, if we consider Laplacian sigma plus delta sigma, it equals to a to the minus 2 delta sigma of x times Laplacian of sigma, right? So if you try to do this, we find the following: that W of sigma plus delta sigma is W of sigma plus like up to the first order, maybe minus up to the first order. We can expand this exponential in the trace, and we get integral from epsilon to infinity dt delta sigma of x. Oh, sorry, I forgot trace. Trace delta sigma of x Laplacian e to the minus t Laplacian. And when we look at this expression, we see that it is actually a derivative of some operator. So it is W of sigma minus integral from epsilon to infinity dt d over dt trace delta sigma of x e to the minus this plus minus t. Why did I put here minus? Sorry. Minus t Laplacian. So, and when t goes to infinity, all the eigenvalues, so all the eigenvalues of Laplacian go to minus infinity. So we can, so this expression vanishes on that boundary, and we are left with this expression on the lower boundary. So we get here W of sigma plus and trace delta sigma of x e to the epsilon Laplacian. And if we rewrite this further, it can be written as so this is some integral operator. This, namely, it is called hit kernel, and so it can be written as And the trace is integral over our complex plane. So it is double of sigma plus integral over d to z delta sigma of, well, let's add z bar, or maybe d to x, delta sigma of x, hit kernel computed at the coinciding points x, x, and time epsilon. So here's the kind of answer. And now the question is who in this K? So this K satisfies the heat equation. So when epsilon is 0, this exponential turns into 1 in a sense to the identity operator. And its kernel should be therefore a delta function. So so we know that k of x y of 0. So write that it is so it is a heat kernel. Because it solves the Laplace equation. It solves heat equation. Laplacian of k of x y t is dt k of x y t. And when when t is 0, it equals to a delta function. Okay, right. And what we are interested in here is the asymptotics of this heat kernel when epsilon goes to 0. So let us like we can also write it as z z0 epsilon. So let us first write the heat equation around yeah, just write this. So it is Laplacian z to the minus sigma of z times d bar k of z 0 t equals to dt dtk. And if you want asymptotics of it, we can say that when z is around z0, this sigma is more or less constant. So we say that So we can say that in this limit it looks like a heat equation with constant coefficient. So k of z 0 t is 1 over what, maybe pi t yeah, check. So, this exponential effectively modifies t. So we can say that it is e to the minus like d bar k is d over d e to minus 2 sigma of 0 t k. So here we then write it in the numerator. And here the most singular term. So the asymptotics of the when z goes to the 0 and t goes to 0. Plus and so on. But if you want to solve, if you want to compute the subject that we need, we need some terms of this expansion. So namely, we should say that like let us put the 0 equals to 0 for simplicity, because it's just notation. We can just change coordinates in some way, and write that this k of z t is some series, right? Let's check. Yeah. So it's 2 sigma of 0 over pi t. So t to some minus f minus 1 f minus 1 over t plus over t times e to sigma of 0 plus sum of 0 of z plus f1 of z t exponential minus 2 sigma of 0 and so on. So we can try to substitute this ansatz into this heat equation, and so it will give some some equations involving these functions f minus 0, f0, f1, their derivatives, and when we see these equations, we can try to find series expansions of these coefficients in Z. And once we get this, we will need to compute k of 0, and we see that then k of 0 and some epsilon will be, so this f minus 1 will cancel, and it will be e to the 2 sigma of 0 over epsilon e to f0 of z plus f1 of f0 of 0 plus f1 of 0 times t times e minus 2 sigma of 0 plus plus all of t squared. Oh, sorry, epsilon squared. So now if we send epsilon to 0 and expand it as a series of epsilon, we will see that it is e to the 2 sigma of 0 e to f0 of 0 over well, actually, we can say that it is f0 of 0 is 0 because it can be found from normalization of this delta function. So actually, it looks like this. So everything can be included into this prefactor. So this looks like e to the 2 sigma of 0 over epsilon plus f1 of 0 plus something of order epsilon. And we actually started from this integral with epsilon equals to 0. And we would like to keep it as small as possible. So we want to send epsilon to 0 at this stage. So we want we don't want higher corrections. So it means that it's enough to compute this hit kernel up to this term. And now let us see what this gives us. So we see that this W of sigma plus delta sigma is equal to so this 0 means actually coinciding points. So it is W of sigma plus 1 over epsilon, this sign maybe, yes, integral d to x, or maybe d to z, delta sigma of z e to 2 sigma of z plus integral with a constant term d to z f1, but maybe what is better, write it as zz delta sigma of z. So what is this term? We don't know at this moment because I don't tell you what is the solution of this heat equation, like how this expansion looks like. But if you look at this term, it is easy to see that this is actually the variation of just the area. So it is 1 over epsilon. Epsilon delta of the integral of d to z e to the 2 sigma. So it means that we could add something like this to the integration measure from the beginning, because the integration measure is defined after constant. So we can add a corresponding counter term, or we can just keep it as is. So there is the area multiplied by some number, which is very big, but there is some number.
What about f of minus 1?
Uh, I will just write the solution of this equation. We can substitute this answer to the heat equation and write some equations satisfied by these f's. And then we can solve each of them. And let me write the answers for them. So. So f minus 1 is equal to z bar plus z bar squared d bar 5 0 plus z squared z bar d 5 0 plus some coefficient this one. Plus complex conjugate plus z squared z bar squared divided by 5 plus 2 third d bar 5. So it's up to 4th order. Actually, we need this with such precision. I used sorry, I used a different notation when computed all this. Sorry, it is sigma. wherever. So it's sigma, and so into the f minus 1, then f0 is so it's minus, I put it with plus sign, so it is a minus 1/3 z bar d bar phi of 0 plus some higher corrections which we don't care about, and the last part is so the last part is f1. F1 is minus 1/3 d bar phi of 0. So we see these two functions actually vanish at 0, and but this one which enters the answer is not vanishing, right?
But we should evaluate the kernel in. Okay, no.
So 0 is z0, it's
Yeah.
same. So maybe if you put here z and z0, then like f1 of z0 equals to d bar phi of z0. So and it's again phi. It's sigma. It's not the scalar field. It's on this factor and the metric. Okay, and now what happens? What happens if we substitute this to this formula? So it is this equals to minus 1/3 d bar sigma. So this so here we should put 1/2, 1/2 epsilon probably. So this term then equals to a variation of the integral d to z of minus 1/6 sigma d bar sigma. And this term equals to this. And this and this computation is called to integrate anomaly. So this transformation of partition function when we change a metric is called anomaly or conformal anomaly. So we can say that it is because the action was metric independent, and the measure naively seemed also metric independent, but it actually depended on this metric. and change of partition function with the change of metric comes basically from the change of measure. So it is called anomaly, and usually this anomaly is just some expression, but in two-dimensional cases, it happens somehow that we can see that it equals to variation of some clear functional. So we can. So the consequence of this is that uh, W of sigma plus delta sigma is mm, maybe how to write it better. We can now say that um, so consequence of this is that W of sigma plus so W of sigma minus the integral over d to z let us write it as 1 over 6 d sigma d bar sigma plus 1 over 2 epsilon e to the to sigma is the invariant. So let me think if it is correct to say like this or not. Yes, so in this way we managed to find the independence of this partition function on metric. Uh, and now let us think what is the meaning of this. And by the way, probably we should do something else. So now if we have this, then we can ask what is the formula for what is the formula for W of sigma? So is it fine? Hmm?
The denominator in front of the exponential.
1 over 2 epsilon, sorry. So
But we have
hmm? Maybe let me erase the definition. Oh, maybe it should. Hmm? Why? But I integrated by parts to make this dd bar. No, here both of them are positive. So
the second term cannot be cancelled by a counter term because it would be the Euler characteristic of the length.
No, it's different. You can cancel it partially, but if you add counter terms, you cannot. So you can cancel infinite part, but as always, we should keep a constant part, because if you add something as a counter term, that we consider it as a relevant operator.
But in principle, I can, like, if, because the counter term that I should add to cancel the infinite part is just an error. The second would be a term which is proportional to the integral of the curvature.
No, you see, it is something non-trivial. It's not the integral of the curvature.
No, that's the point. It can, but there should be the type, because that is like when you expand the curve, the first non-trivial term is proportional to the scalar curvature of the manifold.
Yes, precisely. It is on this one.
Yes. And this cannot be cancelled because it should be a quadratic term.
No, I don't understand. The term which we obtained here is non-trivial in any case. So we obtained that variation of this functional is the integral of delta sigma plus the integral of delta sigma times r.
Yes, and like the first term is like I can cancel it by taking the action.
Which one?
The first one, the term I can cancel by taking the action. Yes.
This?
Yes.
No, but you can cancel the singular part of this, but people usually say that we cannot adjust contra term such that it cancel this term completely. We should keep something something finite. So we can say that on this zero sigma is something like e to the minus 1 over 2 epsilon times plus some finite part. And area times integral d sigma phi e to the minus s of phi. So it's not prohibited to add also some. Yes.
So
Yes.
it's not really a well-defined procedure. I can add whatever constant term I want and shift that constant term. But my point is that if I tune the action from the beginning, I'm able to cancel the first part, the one that causes e to the 2 sigma.
In this one.
Yes, I'm able to cancel.
Well, yes, you can, but I don't know what is the precise meaning of this. Because you see, there are two situations. One is when this coefficient is some zero coefficient, and all the situations are actually equivalent because you can shift sigma by a constant, and this coefficient can be made essentially one. And there is one situation. Another situation is when this coefficient equals to zero. So. I don't know how to say that. No, this coefficient can be put equal to zero. So, when we renormalize it No, epsilon goes to 0, and then we need to choose how to like which term to add here.
No, okay. So once again, so we did a variation of our action in terms of the conformal factor in front of the metric.
Yes.
And we obtain a term which is divergent and another term.
Yes.
With the regulator, and we want to take away the regulator because it's something that we have found by ourselves, is not in theory.
Yes.
So, like, I don't understand like, what should it be the physical meaning of this divergent term? Because then, if I'm able to cancel it with a counter term, it's not physically relevant.
No, but you can just say that, well, we took care of the storm and removed it. But no one can prohibit us to add another term, which is e to the mu times area. It is, from gravitational point of view, it's a cosmological constant.
Yes.
So,
yes. That we can do. But
yes.
okay. So now my point is like, so you're saying that. So when you're saying that this difference is an invariant, what is your claim exactly? Because that I don't understand.
That when we compute double sigma plus delta sigma, it will be the same as like this expression of sigma, and this expression of sigma plus delta sigma will be the same.
In the limit epsilon going to 0.
Well, no, let us say that we made this modification and it turned 1 over to epsilon, we turn it to mu. By doing this. So let us say that we have originally some cosmological constant added by hand. So we say that this partition function of this measure includes this e to the area of our
Okay. Okay. Then you add, okay, so you add the counter term to cancel the routine part up to another constant that you want.
Yes.
Okay, and then you say now it's the variation, and the resulting is the original partition function, I mean the exponential of this, and the Liouville action.
Mm-hmm. Yes. So we can now write it like like this. So here is this.
So in a sense, you are using a normalization scheme to throw away that new fixed super X. Because if I do another shift, like another variation of sigma, I would get again the same term, but then to cancel it, I need to have
Oh, what do you mean?
that if I do another now to add that one invariant under sigma that goes to sigma plus delta sigma,
Mm-hmm.
I should be able to cancel again the part which is divergent. So I have to fix in some sense that right, that constant coefficient that you put in.
What do you mean? It is something which is defined at the beginning. Like we had this epsilon, which is a regularization, which is in the regularization of determinant, and we had here this contraterm, and we put here some mu. So it's so this epsilon is something globally undefined. It's not only for the computation of this variation. So we could say that it is it appears here. So so we should modify it at the very beginning. So and now about us. So we can say something like this, that W of sigma minus W of sigma 0 equals to the difference d to z. No, how to write it better? Maybe let's write it this way. So let us say that we have some sigma 0, and we have and we go from sigma 0 to sigma 0 plus sigma. Which means that, for example, we had originally a metric like sigma 0 equals to a constant, but so it means that we say that our G is e to the 2 sigma mu times G0 mu. Because we need some reference metric to compare the section between different metrics, and I'm doing this because there are some invariants. There is, for example, an invariant which is integral of a curvature, which should be constant, and it is not so obvious how to compute this integral of curvature in the flat metric, because it has a kind of singularity at infinity, but the singularity is not visible in this original chart. So it is better to say that we take some metric G0, which is not necessarily constant, and compute what is the difference between this metric and shifted metric. So, namely, I want to say that W of sigma plus sigma 0 minus W of sigma 0 is the difference of these actions, and it is so it has this term 1 over 6 d sigma d bar sigma plus plus the term where we have interaction between them. So let us write it as this way: minus 1 over 3 sigma d bar sigma 0 plus mu e to sigma e to 2 sigma 0 d to that minus integral d sigma d sigma 0 d bar sigma 0 plus 1 over 6 plus the integral of mu e to the 2 sigma 0 is that. So I'm writing this to show this term. And now what are the meaning of these terms? So if we want to compute the curvature of a metric, or maybe to compute this object, like square root of g g of square root of g times r, it equals maybe up to some sign or factor to Laplacian of sigma. And now what is written here, like so if you say that our matrix, or maybe better to write G0, R0. So if you look at the term integral of d sigma d bar sigma 0 d bar sigma 0 due to that, then this term is actually so a curvature contains second derivative. So we can write it as like d bar sigma 0 times sigma 0 due to that. So if you try to write it in the invariant way, it will be the integral in two variables, d to z, d to w, and here it will be r of z 1 over 1 over Laplacian of z and w, r of w. So this term in the Liouville action is actually local, but if you try to write it in terms of curvature, it will give this non-local expression, R0. So this integral is of course area, zero's area, and we see from this formula that this term is actually interaction between sigma and curvature. So up to some sign which I forgot. So this is sigma times. So we can write it as so this integral can be written as Oh, actually, no, wait. I wrote for some reason the second term, which I cancelled. It should not be written here. Mm, mm. So, mm. No, it should be. Mm, no, this first term cancels. Mm, sorry. Mm. So there is no area. Mm. So. So I want to say that that if you try to write it in some kind of invariant way, you use an original metric, then it will be 1 over 6 sigma minus 1 over 6 sigma Laplacian of sigma uh, minus 1/3 sigma times r0, and here it's Laplacian 0 plus mu e to sigma square root of g0 d to z, and on this area 0. And this is called Liouville action. And I've kept this term, sigma r0. So I started from some curved metric because when G goes to flat metric, this sigma r0 integral sigma r0 turns to some constant, maybe like to pi sigma of infinity. So this is what we saw at some moment. We saw that sometimes we get some background charge, some field which is placed at the infinite point of complex sphere. So. Now, actually, if you want to compute some integral which includes two-dimensional gravity.
Sorry, but what I do not understood what you were trying to say when you rewrote the integral of d sigma naught and bar sigma naught in terms of r and the sinusoidal of delta.
No, I'm just saying that this term in the like when we expect some functional of metric, we usually expect to have some curvature derivatives, some invariant combinations of this kind. Right? For example, if you have a usual Einstein gravity, then it is an integral of a curvature plus a cosmological term, lambda times volume. But such naive terms like like integral of curvature is constant. It depends only on topology. But it turns out that in 2D we can write this Liouville action, and it is, I don't know how to call this precisely, something semi-local. So it can be written in terms of curvature. Like it is not obvious from this notation what is the diffeomorphism invariant expression for the section, because this is written for some fixed gauge. It is written for diagonal metric. And how to write it if you switch to non-diagonal case. And so to do this, we can express it in terms of scalar curvature and Laplace operator and write this expression. And it's a kind of bonus for us that when metric is diagonal, this expression can be written in a local way. And, why? What?
Basically looking as a conformal factor next to a flat metric, you get an object which is local, but in coordinate free notation is non-local object.
No, I don't think that it should be weird because, for example, is it weird that the integral of a curvature, which is some local object, becomes just a number?
No, I wouldn't say so.
Hmm.
I wouldn't say that this is good, to be honest, because I mean, I expect that somehow I'm able, in some cases, to recover topology by integrating local objects.
Yes. But in this case, it's just expression of phenomenon that locally this this curvature can be written curvature times. Actually, I forgot to write here. So square root of d0, square root of d0, it is included in the metric. So here we see that a scalar curvature is dd bar of some function. So scalar curvature times square root of metric can be written in this way.
In this way, I mean, I will have a correlation between product resources at arbitrary distances.
Well, not arbitrary because better to say that we live on a compact surface to make everything well defined.
Well, I mean, the area is not.
Hmm?
But no,
Mm.
in any case, like if I will, if I look at correlation function of curvature with a curvature or something like this, I'm gonna get something which is like really slowly decaying in some sense.
No, why? If That's a good question, actually. So if we put mu to 0, then what I think. Mm. Mm. So curvature sigma is a logarithm z minus w. absolute value. So if you take second derivative, if you take Laplacian of just one sigma, then this correlator becomes a delta function at the coinciding points. But for the Liouville, for the actual Liouville, probably it is not true. Like we cannot say that uh, we cannot say that this correlator has dot function. Also, it will be something. Mm, but no, there are some products will be, of course, this one. So it should be something regular when these points collide. Mm, but I would not say that it is just zero.
No, 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 no. Why zero? I'm saying that the correlation function, when the points are really close, they should be the same as
Yes. No, I mean that if you then try to compute Laplace, try to act with Laplacian, probably we should say again a delta function like this point.
okay, okay, but this is like my problem is this because we are using as degrees of freedom sigma, right? That
Yeah.
are some I don't know h fixed degrees of freedom in some sense.
Mm-hmm. Yes.
But if I chose gauge invariant degrees of freedom like the curvature and whatever, do they like if I compute like correlation function, do they look local objects? That is my
But how do you define local?
I mean
It's CFT, like any correlation function decays like some power or logarithm, so they don't go to zero exponentially fast. So everything is
yes, but like my problem is
strongly.
that when I have a non-local action, like an action in which I have a correlation kernel, so interactions are point wise.
Hmm.
I mean, I imagine that correlation function behaves weirdly when I separate the operators.
Mm.
Because in some sense, like they still interfere like this.
So. Mm. Oh, you don't like that the kernel in the action is not a Laplacian, but is inverse Laplacian. But if we switch to momentum representation, then it means that grain function is just a Laplacian, like k squared, and its Fourier transform is second derivative of the delta function. So it is the opposite. It is something super local. Mm.
Here is like when you write,
Mm.
like you are
In the core.
in a scalar frontier,
Mm?
and you write the action in terms of the yeah, of the Green
Mm-hmm.
function coupled to like you have like a scalar coupled to an external current. Yes, but that
Mm-hmm.
yes, but that is an effective the theory is strict. No, no, I'm saying that this is the effective action that you use to compute correlation function. It's not that you do the path integral with the sources. No, because the while the sources are not numbered. Into that, that's the not here, not here, not here. Not yet, but then you want to do a QFT with that, with the G0. No, with sigma. And here the source is G0, R0. I I assume that those are like sources that are not as a background metric. Okay, okay.
Okay, we go. Ah. Mm. So and now actually if if we want to compute some actual so this way we know this explicit dependence uh, of a partition function on this uh, scalar factor. And if you think about some kind of two-dimensional gravity or about string theory, where we need to integrate over all possible metrics. And then we should also care about proper gauge fixing, because here we just said that G is Z and the G Z bar are 0, but if you do a proper gauge fixing, like we should say that our metric is G ZZ equals to what uh, d epsilon probably and G z bar maybe d epsilon bar yeah like this equals d bar epsilon. We also add delta functions of G. We add delta function of G Z Z delta of G Z bar and integrate over epsilons over like the epsilons and so on, and we see that operator which maps from this vector which maps from tangent space to diffeomorphism to tangent space to matrix to space of matrix is D and D bar and so for the Popov determinant is the integral over dB dc e to the integral b d bar c plus like b bar c c bar plus b bar d c bar, and this c is so And this C is a vector field because this is the operator acting to vector fields. So delta of C is 1, 0, or minus 1, 0. Delta of B is 2, 0. Hmm? GZC is 0 and GZ bar is also 0. So, hmm? So it's determined. Yes, it is what happens with a metric when we do some coordinate transformation, like z bar goes to uh, epsilon to z plus epsilon z bar plus epsilon bar. So I'm saying that if we start from this diagonal metric with some scalar factor and try to perform a coordinate transformation, arbitrary coordinate transformation, like non-conformal one, then we get necessarily the of diagonal components, z and z bar, right? And they are given precisely by this non-homomorphicity of epsilon. So because you remember G mu nu goes to G mu nu like to G mu nu plus epsilon rho d rho G mu nu plus or maybe plus 1/2 d mu epsilon nu plus d nu epsilon mu, if I remember correctly. So of diagonal components do not have the derivative term because they were 0 originally. But they get some corrections due to this derivatives of the transformation. So if you perform non-conformal transformation, if epsilon has if epsilon is not homomorphic and epsilon bar is not anti-homomorphic, then our metric receives two corrections, which are precisely the derivatives. Yes. And as we know, so I don't want. That makes sense to tell the story about Federico codeterminant, or you heard it somewhere. So, what do you think? Ah, oh, I can. Oh, oh, okay. So let me tell this maybe. Uh, so the story is the following. 1. So suppose that we have some action S of I don't know S of what variable? Let us call it A. Such that S of G of A it has some symmetry. This G is in some group G. So and we want to compute the integral, and the problem can be that this group is infinite dimensional. So we want to compute the integral e integral over dA e to minus s of A. And so to do this, we insert here the following object. So let us define. Let us take some function g of A. F of A. So let us define first the following quantity: a delta of A by definition is delta inverse of A. And by definition is the integral over our group dg or over G. Delta function of f of G of A wait, maybe it is easy to be lost in this brackets. So let us use this notation for the group action as a superscript. Delta of f of A G transformed. So there is the following statement that if we transform A here, it will equal to the integral over this group dg delta of f of A G H. And then we can change the integration variable and because this measure is invariant. So it is integral over GH delta of f of A G H. Maybe it is also HG, the multiplying this order HG. Yeah, like this, and Mm, so we change its variable, and we see that it is the same as just delta of A inverse. So it's some gauge invariant object. Mm. Okay, when we have so we have such delta of A, and we can now say that if I put it here, delta of A, then it will be something gauge invariant. Using this trick, we can rewrite this integral which we want to compute as the following integral. It is integral over dA. Then we insert identity. And insert here integral in dg delta of A delta delta of f of AG. E2 minus S of A. Maybe better to write it as functional. I don't know. No. So here it is this one. Yeah, so we have this integral, and now we can do the following. We can notice that this object is a gauge invariant. So this is a group of gauge transformations, I call it this way. And this is also gauge invariant. So we can write it as integral over dA, integral over dg, delta of A gauge transformed, delta of f of A gauge transformed, E2 minus S of A gauge transformed. And finally, we just say that integration measure is also a gauge invariant, and remove this and add here this g. So our integral after this turns into the integral of integral over dg over this group times the integral in dA. Some dA delta of A e to minus S of A. So we see that this infinite volume of the gauge group decouples, and we can say that it is just some number. So it is some constant, some infinite constant. So this equals to volume of G. And we don't care about this. We say that, oh, sorry, I forgot to add this delta function. Delta f of A. So now let us apply it this to our situation. maybe we can erase this hit kernel. So so this delta of f of a g. In our situation, it will be a delta function of g z z at times a delta function of g z bar z bar. So if you want to integrate some e to minus s of some action which depends on matrix, then divided by volume of diffeomorphisms. So we can say that it is integral of integral over a scalar factor times times this determinant times this Faddeev-Pohl determinant, which depends on sigma. Times e to minus s of e to the to sigma, like dz bar, because in principle we had here this integrals over d g z z d g z bar delta g z z delta g z bar, right? In principle we had these integrals, but they disappeared. Maybe I don't know. Maybe it is better to write. Oh, is it clear what I want to say or not? Oh, no. Let us better write it like this. So we have some integral over this matrix. So g z z bar d g z z d g z bar z bar. We have this delta of g, which should be computed. We have e to minus s of g, And we have the delta functions of g z z and delta of g z bar z bar. Let me check.
Conformally flat
Yes, yes. So, and this integrals can be computed. So we just say that this integral is the integral over conformally flat matrices. D It is some integral over d sigma delta of e to the 2 sigma e to minus s of e to the 2 sigma. And the only question is what is this the only question is what is this determinant. So to compute this, we should remember the definition. Like so we need to say that the integral of delta of g, like really of e to the 2 sigma. So delta of e to the 2 sigma times integral over epsilon, like epsilon bar in so we integrate this product of the epsilon bar delta of g z z plus d epsilon bar delta of g z bar plus d bar epsilon. But this actually equals to 0 because we are interested in the value of the determinant only on the diagonal, only for the diagonal metric. So it is 0. So and when we compute this, we can say that so integral of delta function of something is what? It's 1 over the determinant of derivative of this. So we find that this integral is 1 over determinant of d, 1 over determinant of d bar. Is it fine? And this operator, these operators act on the vector fields because this is component of the vector field. Like it's a formula that integral over dx delta function of some a times x equals to 1 over determinant of a. Is it? Hmm? Oh, it's two determinants for one operator and another operator. Sorry, I forgot to write this. Yes, a delta of e to the 2 sigma, and all this equals to 1, right? So if you have this, then we can say that people usually raise those determinants to the exponential using a fermionic integral. The next step now is to say that delta of e to the 2 sigma equals to integral over dB and dc e to plus or minus, it does not matter, integral b d bar c plus b bar dc d to z. And since we use the same operator which we obtained here, the nature of the C is the vector field, and the nature of B is to form, because this operator acted from the vector fields to some objects which had two lower indices, so there were two forms. And this is why dimension of B is to 0, and dimension of C is minus 1, 0. Right? So, is it fine? Yeah, thank you. Hmm? Well, I didn't know. Probably I'm not a big specialist in this, but probably people call anti-ghost something different. Probably it is something which appears when we overfixed the gauge. No, I would call them just ghosts, but I'm not specialist. Maybe wrong. So. Because like let us look at the action of this of this of this debar operator. So our vector field is like is epsilon d plus epsilon bar dz epsilon bar dz bar. And this is kind of invariant object. It means that this epsilon has dimension, so dimension of epsilon is -1, 0. And for epsilon bars, it's opposite. And so uh, uh, maybe there are two ways to think about this. Let me think. Or maybe let us think this way. So we know that this epsilon is the object of this type. So our operator d bar acts on the vector fields. So uh, when we start to write this, if we want to represent the determinant of this operator as this fermionic integral, the nature of this object where it acts should be the vector field. And and now let us compute the dimension of this product. So dimension of d bar c is maybe better to write in this notation, like conformal dimension. So conformal dimension of d bar c is a -1, 1. Dimension of d to z is -1, -1. So in order, and we want that a dimension of d bar c, like b d bar c, d bar c, d to z should be 0, 0, 0. And from here we can conclude that a dimension of b is 2, 0. So this is how to write the determinant of the bar operator that acts not on a function but on the vector fields. So we should have some fermionic functions which behave like vector fields, and we should also have some counterpart to integrate this with, and those are two forms, because only in this case this action is conformally invariant. And maybe we can also think about this this way, that this to form is some relative of this component of G, because it is also to form to zero form. So in a sense that this this is the space where this operator acts too. And I don't know how to phrase it. Hmm? Yes. Yes. So, yes, this is what I'm trying to say, but mm, yes, because this operator, uh, uh, yes, because this matrix which is written here, so this index which is substituted into the delta function is the index corresponding to form, because we write a condition that delta of GZZ is 0. And this right index is the index corresponding to vector field. So, uh, so yes, to this way, um, maybe it's uh, maybe it's the answer actually. Oh, so sorry, I'm run out of time. Uh, so the consequence of this is that when we want to integrate a biometric, then we can write this integral, but should also we can write the integral over the scalar factor, but we also appear we also get this Fedorov-Popov determinant, which is BC system. And it is also a CFT, of course, and this and its central charge is minus 26. Mm. So we will maybe compute it some next times. Mm. So and we'll discuss more about the Liouville theory. And when we get this, we can also say that, so I wrote e to the minus 2 sigma here. But the question is how it depends on sigma. And the answer is that mm, here we computed what happens with a CFT that has a central charge 1, but it is some universal statement, because if we combine several free bosons, this conformal anomaly will add up, and the charge, the central charges also add up, and the only object that so it's the only object which can be written as conformal anomaly. So we can say that and there is the same formula for arbitrary central charge. We just should put central charge in front of this integral. And particularly when central charge is 0, then there is no conformal anomaly. Hmm. So we can also say that this integral can be written as an integral in the flat metric times minus 26 and times this Liouville action. So uh, so in general, we get something of this kind. So if we had some S, which depended on some field phi, and which is not necessarily a scalar field and a metric. From here we get the integral over like integral d0 phi d0 b d0 c and the integral in d like sigma. When by zero I mean some background matrix, and here we get a minus s bc of bc minus s of phi of g, s of phi can do g0 minus s of phi and g0 original metric plus s Liouville of phi g0 of sigma g0. So we get something like this, and it looks like some CFT, but we know that since this is that G0 is just some reference point, then we know that central charge of this, and we know that this integral should not depend on background metric. So it is G0 independent. And if it is zero independent, it means that a central charge of this ABC system plus central charge of this matter plus central charge of Liouville, which we will compute the next time, should be zero. And then we can study on this. For example, one way to achieve this is to say that we have 26 scalar fields and one BC system and no Liouville, and it will correspond to bosonic string. Yeah, so maybe that's all. Are there any questions about this? Yeah, so thanks for your attention.